So this is the first video that I've prepared in preparation for the Quantitative Data Analysis workshop. And in this video, I'm going to briefly review the challenges in using mortality data as a measure of studying health inequalities. And I'm going to be introducing standardisation as one way in which we can have more accurate comparisons of health inequalities using mortality data. So you probably might be familiar with the challenges of comparing mortality data between populations. Just to give you a kind of a classic example here, if we take the most straightforward and simplest calculation of mortality, which is the crude death rate, it's very difficult to make accurate comparisons using this measure between populations, whether that's countries or subpopulations. So the crude death rate is a very simple calculation. To calculate it, we just take the total number of deaths for a population at a particular time, and we divide that by the total population at the same time. And we usually multiply that by 1,000, or you might come across death rates that are expressed per 10,000 population, or even by 100,000 population. Crude death rates really tell us very little about the underlying mortality in the populations that we are looking at. So to give you an example here, the crude death rates in 2020 for 3 countries, Afghanistan, Bulgaria and Japan. As you can see, the country that was calculated had the lowest crude death rate was Afghanistan, with a crude death rate of 7. Bulgaria was calculated to have a crude death rate of 18, and Japan a crude death rate of 11. And the simple reason for these differences in crude death rates, which is certainly not what we would expect with our knowledge about the countries, is all to do with the age structure. So here I've just illustrating the population pyramids, which I hope you are familiar with, for the 3 countries, Afghanistan, Bulgaria and Japan, whose death rates I've previously shared with you. So Afghanistan, which is the country on the left, is a classic example of a country with high mortality and high fertility. So this means that a larger proportion of its population are in the younger age groups. And if we compare that to Japan, which is on the right, Japan is a classic example of a country with low mortality and low fertility. So a much larger proportion of people are in the older age groups. And because most deaths tend to happen to older people, we find higher crude death rates in older populations, which is why Japan has a much higher crude death rate than Afghanistan, even though the underlying mortality might be higher in Afghanistan. The country, though, that has the record at the moment of having the highest crude death rate in the world is Bulgaria, and at the moment it tends to move around Eastern European countries. This is, as you can see, it's got a particularly top-heavy population age pyramid, but here in Eastern Europe we're not just looking at the impact of age structure, but we're also looking at some interesting things that have been happening around mortality, and particularly high mortality of men in the 60s, in their 60s and 70s. So there is a bit of an underlying course going on there, but generally the reason that we can't compare either the total number of deaths or crude death rates is because we need to take age structure into account. So if we can't compare crude death rates or the total number of deaths, if we want to use mortality as a way of measuring health inequalities, we either need to look in detail at age-specific death rates, or we can standardise death rates, or we can compute life expectancies. What I'm going to be just covering in this video is looking at age-specific death rates and standardised death rates. In the second video, I'll be looking at life expectancy. So because of the problems in using crude death rates to compare mortality, a first stage in using mortality to analyse differences in health inequalities is to calculate age-specific death rates. And these death rates are calculated by the Office for National Statistics for the UK. For example, the death rate for people aged 60 is simply the number of deaths in a year to people aged 60 divided by the mid-year population of people aged 60. Just to point out, there's one special age-specific death rate that's known as the infant mortality rate. Here the denominator is slightly different because to calculate the infant mortality rate we take the total number of infant deaths in a year to infants aged less than 1, but the denominator is the total number of live births, so it's not the mid-year population. If we want to compute summary methods from our death rates, one of the most straightforward things to do is to standardise death rates by age structure. And there's two different ways which we can do this, direct or indirect standardisation. For direct standardisation, we take the age-specific mortality rates from the populations that we're interested in comparing, and we apply these to a standard age structure. And indirect is the opposite of that. This time we take a standard age-specific mortality rate and we apply this to the different age structures of the populations that we are interested in comparing. So I'm just going to go through how we do standardisation, starting with direct standardisation, and I'm going to be working through a resource that I've taken from the Faculty of Health website, and I'll put the link on the KLE if you want to spend more time looking at how you do standardisation. So for direct standardisation, we take age-specific death rates and we apply these to a standard age structure. And the example from the Faculty of Health website uses two hypothetical populations, country A and country B. Just to summarise, country A, looking at the data at the bottom in bold, has a much larger population of 14 million and a higher accrued death rate of 10.5 deaths per 1,000 population, while country B has a smaller population of 2,170,000 and a lower death rate of 7 per 1,000. But the reason that we have these differences in overall accrued death rate do not correspond to the age-specific mortality rates, where if you go further up the table and you look at the rate per 1,000 population for country A and country B, you can see that in all three age groups the mortality rate is lower in country A than it is in country B, though the difference by the time we get to the older age group is much smaller. So we can see that country A does actually appear to have lower mortality, but because it has a different age structure, it has an older age structure, the accrued death rate suggests that the mortality is greater. So this is how a direct standardisation method can be used to compare the mortality in country A and country B. What's happened here is a standard age structure has been taken, and the same age structure is used for both countries. This standard age structure has 100,000 people in age 0 to 29, 65,000 people aged 30 to 59, and 20,000 people aged 60 plus. So in the column for country A in this table, what's happening here is the age-specific death rates for each age group is applied to that standard population to give an expected number of deaths that would happen in country A if it had the standard age structure, and exactly the same as is done for country B, where this time the age-specific death rates for country B are applied to the same population structure. This gives the total number. This gives the total number of deaths in each age groups, and we can then sum that total number to give the total expected deaths for country A and country B if they had the standard population age structure. And you can see that country A has a lower expected death rates. It has expected death rates in total of 1,314, while country B has higher expected death rates of 1,777.5, has higher total expected deaths. So we can then work out an age-adjusted rate where we take the expected deaths and we divide it by the total population for the standard age structure. And the total population in the standard age structure is 185,000. So that we can see that the age-adjusted death rate for country A works out at 7.1 per 1,000, and the age-adjusted death rate for country B works out at 9.6 per 1,000. We can then use those two adjusted rates to create an age standard rate ratio, where we divide the age adjusted rate for country B by the age adjusted rate for country A, and that final figure of 1.35 gives us a measure of the differences between mortality in country A and country B. It gives us a measure of how much greater the mortality is in country B compared to country A. The second approach to carrying out standardisation is indirect standardisation, and this is a little bit trickier to use. So if you have the data to do direct standardisation, so if you have age-specific death rates, you would do direct standardisation. You only ever use indirect standardisation if you do not have the data available for direct standardisation. And by that I mean if you do not have age-specific death rates for the subpopulations that you're interested in. And this sometimes does occur. For example, if you wanted to compare the mortality rates of two occupations, you might not have age-specific death rates for two populations. But you might have the total number of deaths occurring to people in a particular occupation, and you might have the age structure of people working in a particular population. And with that data, you can carry out indirect standardisation. So you will see examples of indirect standardisation, which calculates a key measure which is called the standardised mortality ratio. You will see examples of that in the literature. So in this example here, it is looking again at country A and country B using indirect standardisation. And for indirect standardisation, you take a standard set of age-specific death rates and apply it to different populations. So to do indirect standardisation for country A and country B, we take a standard set of age-specific death rates and apply it to the age structure of country A and country B. And in this particular example, the standard age-specific death rates is the same as the age-specific death rates for country A. So I'll explain that. I hope that's not too confusing, but I'll go through the table. So if we look at the column for country A, what the calculations that are going on in that column are we taking the age-specific death rates and we're multiplying it by the population in country A. So the age-specific death rate for the population aged 0 to 29 is 0.0012, and that's been multiplied by the population aged 0 to 29, which is 6 million, and that results in 7,200 deaths. In the population aged 30 to 59, the age-specific mortality rate of 0.0036 is multiplied by the population aged 30 to 59 in country A. That's 5.5 million, and that gives 19,800 deaths. And again, for the population aged 60 and over, the age-specific mortality rate, the standard age-specific mortality rate is 0.048, and that's multiplied by the population of that age in country A, and that's 2.5 million, and that gives 1,200 deaths. So the total number of expected deaths is 1,470. In the column for country B, we take exactly the same schedule of age-specific mortality rates, and this time we multiply those against the total population in each age group for country B. So for the age group 0 to 29, if we take the age-specific mortality, standard age-specific mortality rate of 0.0012 and multiply it by the total population of country B aged 0 to 29, that's 1.5 million, we get 1,800 deaths. And if we repeat that for the other two age groups, we find that the expected deaths in country B, if it had the same age-specific mortality rates as country A, comes out at 9,540. Now, that in itself is, we cannot actually in itself compare those particular numbers. What we need to do in order to be able to compare country A and country B is see how those expected deaths compare to the observed deaths. Now in country A, the expected deaths is the same as the observed deaths because we've taken the age-specific mortality rates of country A and applied these to the population age structure of population A. So it's exactly the same. But in population B, there's a big difference between the expected deaths and the observed deaths, because the observed deaths are the result of the age-specific death rates that exist in country B applied to that population, while the expected deaths is the number of deaths we would expect to have if country B had the same age-specific death rates as country A. And as you can see, for country B, the number of expected deaths is lower than the number of observed deaths. And what we do to calculate the standard mortality ratio is we divide the number of observed deaths by the number of expected deaths. And we usually express that ratio by multiplying it by 100. So for country A, the ratio is 1 or 100, and for country B, the ratio is 1.6 or 160. So again, we can see that country B has higher overall mortality than country A. Now I've gone through that quite quickly because I just really want to introduce the idea of standardisation to you, because it is something that you might well come across in the literature. I would recommend though, if you want to spend more time understanding standardisation, that you go through the example on the Faculty of Health website, which is where I have taken these examples from. So that was a quick summary of standardisation. It's the end of the video. In the next video, I'm going to be talking about life expectancy.